Namaskar, myself Soham Dave, enrollment number 25 MCD005. I study in M.Tech Data Science, Nirma University. The topic for my term paper submission for the subject Data Structures and Algorithm is a comparative algorithmic analysis survey of graph convolutional networks, which are also called in short GCNs. Now, before moving towards the paper, let me introduce you with the concept of graphs. What are graphs? Graphs are a structure which has n number of nodes which are connected with number of edges, and each node is connected with some other nodes through the edges. So that is called the graph structure. Now, what was the need to introduce the graph convolutional structures when we had the CNNs, the convolutional neural networks? The CNNs and RNNs work better when we have data in a streamlined structure or like a grid structure, like images. In images we have pixels as a grids. So the CNNs and RNNs works better for the grid-like structures. But what if we have a data where each and every data point is connected with some or the other rule? It is connected with some other data point and it creates a structure like a graph. For an example, let's take the example of social media networks. So in social media networks, what we have experienced, that one person is friend of other person, and that other person is also friend of n number of people. So that's how the whole social media chain has been created. It's like a graph. So in today's era, the data which we are collecting, it is more graph oriented than the structured grid oriented data. So that was the need to innovate something like graph convolutional networks. Now, before moving to the graph convolutional network, let me tell you an interesting fact that the day I started researching on this topic, I came across multiple research papers, and I have experienced that when we read one research paper and we go in the citations of that particular research papers, we find n number of other research papers which are referred in that paper. So when we click on some or other the reference papers, in the reference paper we also find some citations, and from those citations we can also move towards some other papers. Eventually all the papers, they consist the same knowledge base, but the way they are connected, the way the whole citation process is like structured, it is also called like we can call it a graph. So yeah, that was an introduction for graphs. Now let's move towards the graph convolutional networks. So in graph convolutional networks, in this paper, two terms will be there which I want to clarify before I start the paper. So first of the term is the feature matrix, and second is the weight matrix. So what is the feature matrix? For each and every node, there are some features involved with that particular data, and those features are mentioned in the matrix format, that okay, this particular data point, this particular node has n number of features, and this particular node has these n number of features, and another one extra point I want to add is adjacency matrix. What is adjacency matrix? As we have discussed earlier, that each and every node in a graph is connected with some other node. Then how can we define that which node is connected with which other node? So the adjacency matrix, it is created in such a way that it tells us that this node of the graph is connected with this graph. So adjacency node is eventually giving us the idea about which nodes are adjacent to each other. And the third point which I want to clear is the weight matrix. The weight matrix shows us the importance of each and every feature. Like some features we want it like they are the more important features, so their importance will be higher, their weight will be higher, and that weight will be mentioned in the weight matrix. So these are the common terms which we have used in the paper. So now let's begin with the paper, and let me take you to the graph convolutional networks. So this is the abstract which I have just told you. It is like the same thing is written in the abstract and introduction. In this paper I have compared 30 various algorithms which are based on the graph convolutional networks, and which use the graph convolution networks. And the key part of this paper is the way I mentioned how graph convolution networks are becoming a next big thing. And another thing is that what is the problem with the graph convolutional networks? The main problem with graph convolution networks is their complexity, is their computational power that it takes. Because the graph structure is already very dense and already very difficult to work with rather than the grid-like or the structured data. So it takes the more computational power, more computational complexity than the normal data. So this is the abstract as we have discussed earlier. This is the same thing written in the abstract and algorithm introduction. So I also told you how graph convolution networks work, and so now the introductory part is now finished. So now let's move towards the paper itself without wasting much time. In this paper, I have partitioned the algorithms in 7 different domains, because we cannot compare one domain algorithm time complexities with other domains. So I have partitioned it in 7 different parts. In each domain we are having a number of algorithms, a number of papers which I will be citing here. And after all the parts there is one table mentioning all the time complexity combined for that particular domain. So this will be going to be the structure of our paper. So now let's move towards the paper and let's understand how graph convolutional networks work for different domains. So the first domain which we have taken is traffic and transport prediction. For traffic and transport prediction, our first algorithm is LT-GCN. LT-GCN is also called as layered training graph convolutional network. The layered training graph convolutional network proposed by Lee and Su is designed to reduce the computational complexity and training time of traditional GCN models when predicting traffic in large-scale communication networks. Instead of training all layers simultaneously in the standard GCN, LT-GCN uses a layer-by-layer training approach. So where only one layer's parameters are updated at a time while keeping all the other layers frozen. This significantly reduces the training time while maintaining nearly the same prediction accuracy as the original GCN model. So what they are doing is they are processing it layer by layer, as we have discussed earlier. In graph convolution networks, we also have layer by layer data. Like in layer 1, there will be going to n number of graphs. Out of that n number of graphs, we will gain some knowledge and we will move further. We will convolute to the second layer, and that's how we go layer by layer. So in general GCN models, all the layers work simultaneously, which increases the computational complexity. But in this layer-wise module, we are trying to reduce that computational complexity. So now let's move towards its algorithm. And its algorithm is stating that h is equal to, this is sigmoid function a cap h into w. Now what it is trying to say is, first of all, what is a cap? A cap is our adjacency matrix. But we have normalized the adjacency matrix because adjacency matrix, why we have to normalize the adjacency matrix? Because some elements in some nodes which are having more number of neighbors, they should not dominate the nodes which have the lesser number of nodes, we can say. That's why we are normalizing the adjacency matrix, and that a cap is a normalized adjacency matrix size n cross n. H of L is the node feature matrix. As we have mentioned earlier, the feature matrix, the weight matrix, all will be here. The feature matrix is size n cross f. The f here states the input features. Then WL is the weight matrix with the size f cross f. Now the first step in the GCN, what it does is, it does the aggregation, like as we have A cap into H of L. A cap is an n cross n matrix and H of L is n cross F matrix. So as we know, for dense graph we will have big O of n square into F complexity, and for sparse graph where the number of edges are lesser than the dense graph, because in dense graph every node is connected to each and every other node, so that's why there will be a big O of n square into F. Where in the sparse graph with m edges, here the number of edges are denoted as m, the complexity of that step will be big O of m into F. Now next step will be the transformation operation. In the transformation operation, whatever result we are getting for this step, we will multiply it with the weight matrix. So matrix multiplication will be applied here. N cross F matrix we have, and we will multiply it with the F cross F weight matrix. So it will give us the time complexity big O of n into F square. We have completed the step 2. Now we will move towards the step 3. What is stated in the step 3? Step 3 is just an activation function. In machine learning, for each and every element of that particular matrix, we are applying a activation function. So in this step also we are applying the element wise operation on n cross F matrix, and for each element the activation function sigmoid will be used. For n cross F matrix there will be n cross F elements. That's why the complexity of that particular step, it will be big O of n into F. So the final time complexity here for dense graphs will be big O of n square into F plus n into F square. Rather, if we are having sparse graph with lesser number of edges, we will have, which are the typical networks as it's mentioned in the paper, it is big O of m into F plus n into F square, where the n is the number of nodes in the network, m is the number of edges in the network, f is the feature dimension, number of features per node. So this was the algorithm 1. Now let's move towards the algorithm 2 in the same domain of traffic prediction. The second algorithm is STAT-GCN. What is STAT-GCN? STAT-GCN denoted as spatial temporal attention dual graph convolutional network. As the name suggests, here we are going to have two layers of graph convolutional networks. So a spatial temporal attention dual graph convolutional network, STAT-GCN, is proposed by the author, enhances the traffic flow prediction by using a dual graph structure that captures both static spatial relationships and dynamic temporal patterns. Spatial are the geographic data and temporal is the time series data, as we know. The algorithm uses Chebyshev polynomials to approximate the spectral convolutional filter and incorporates a spatial temporal attention mechanism to dynamically adjust the influence between nodes based on the traffic patterns. This approach better captures the complex dependencies in traffic networks compared to traditional methods. Let's understand it with the algorithm. This is the algorithm overview. The core GCN operation uses the Chebyshev polynomial approximation with the attention. What is the attention? Attention factor is mentioned as S dash here. We will go with the what each and every variable is trying to denote here. Let's understand. The f of A will be the summation of all the k. K is a Chebyshev coefficient here. So k will be for all the k values. We are going to have theta of A and tk of L, and this is element wise multiplication with S dash followed by the x function, and we are having the tk of L is the Chebyshev polynomial in order of the k. K is the Chebyshev order as we have discussed. S dash is the attention matrix. S dash is an attention matrix with the size n cross n, and X is the input feature matrix with the size n cross f. Now first step here is to compute the Chebyshev polynomial terms for each order k for 0 to k minus 1. Each tk of L computation on sparse graph will take order of m. M is the number of edges here. total for all k terms will be order of k into m, because for each tk of L computation it is generated in order of m. So for all the k terms it will be order of k into m. Now the second step will be element wise multiplication with attention. So this attention matrix we have S dash mentioned in the earlier stage, which is here. So for each k terms we are applying n cross n element wise multiplication with n cross n other matrix. The complexity of per term for sparse matrix is we are having order of n. So hence the total will be order of k into m. The third step is weighted sum of k terms. So now we will make the summing all the k matrices of size n cross n. It will create the complexity again order of k into m. So the total complexity, now we are still remaining two steps. The step 4 is the apply the filter to features, which is again the matrix multiplication between n cross n, which is f of a matrix, and n cross f, which is the input features matrix. The sparse matrix multiplication here will be order of m into f. If it was a dense graph, it would have been order of big O of n square into f. Apply across time window. All above operations repeated for t time steps. Like so, all of the steps which we have mentioned here, all of them will be repeated for t times. So we will multiply the whole equation with t. So the final time complexity will be order of t into k into m into f, where n is the number of nodes, vertices in the road network, m is the number of edges in the road network, t is the time window size, number of historical time steps, k is the Chebyshev polynomial order as we discussed earlier, f is the feature dimension or the number of features per node. So this was our second algorithm. Now let's move towards the third algorithm. Third algorithm is GCN LSTM, graph convolutional networks with long short-term memory. What the algorithm is stating is the GCN LSTM combined model proposed by the author integrates GCN with LSTM, the long short-term memory networks, to predict the traffic flow at the flow direction level, individual turning movements at intersections. The GCN component captures spatial features by modeling the road network's topological structure, while the LSTM component handles the temporal dependencies in the traffic flow time series. This combination exploits both spatial correlation between road segments and temporal patterns, providing more accurate predictions for traffic signal timing optimization. The time complexity calculation will be like this. The algorithmic overview is given here. The GCN layer uses first order Chebyshev approximation. The Chebyshev approximation is denoted as H for the layer L plus 1 will be equal to sigmoid activation function. Now this particular term, this d tilde raised to minus 1 by 2 into a tilde into d tilde raised to minus 1 by 2. This d tilde is a degree matrix. Each node is having some degree. Each node is connected with n number of edges. So each node has some degree, which is how many edges from that particular nodes are emerging. So that is the degree of that particular node. So this degree matrix is showing the degree for each and every node. Why we are doing this? So as we have mentioned earlier, that the adjacency matrix needs to be normalized because some nodes are having the larger number of neighbors which can manipulate our results. So to normalize that term, we are using this formula, and after this term, the adjacency matrix will become A cap. H and W again feature matrix and weight matrix. This is the simplified version of the same Chebyshev. After the Chebyshev approximation, this will become, as I have mentioned, the A tilde here becomes A cap because of this whole terminology. So now our adjacency matrix is normalized here. A cap is a normalized adjacency matrix of size n cross n, sparse with m non-zero entries. H is the feature matrix of size n cross f, and WL is the weight matrix with size f cross f. Now what this algorithm is doing is, in first step it is doing the feature transformation. For feature transformation we are doing the feature matrix into the weight matrix. So the matrix multiplication will be here n cross f matrix into f cross f matrix. The complexity will become order of big O of n into f square. Then the second step is happening, whatever result we are getting of this step, we are multiplying it with our normalized adjacency matrix. The matrix multiplication will be n cross n, adjacency matrix, n cross f, the result matrix. For sparse adjacency matrix with m edges, the time complexity for this calculation will be big O of m into f. The third step is the activation function. Activation function happens element wise every time. We have to remember it, that the activation function which is element wise, so it is an element wise operation on n cross f resulting matrix, which gives us the complexity of big O of n into f, which is negligible compared to previous step, because in previous step we are having some polynomial terms as well. So this step is negligible. So the final time complexity for this algorithm will be big O of m into f plus n into f square. Here the n shows the number of nodes, intersections in the traffic network. M is the number of edges, road segment connecting intersections. F is the feature dimension, like number of features per node. So this is the time complexity for the GCN LSTM algorithm. Now let's move towards the next algorithm. Next algorithm is MD-GCN. MD here is multi-scale temporal dual graph convolution network. So the word dual here suggests that it also uses two layers of GCN. The multi-scale temporal dual graph convolution network proposed by the author addresses traffic flow prediction by combining multi-scale temporal convolution with dual graph convolution approach. The model uses the graph stage to capture local spatial correlation between neighboring nodes and mixed hop propagation to capture global correlation. So what we are doing here is we are getting the local relation as well as global relation. So for the two steps of GCN, for two layers of GCN, for first layer what we are doing is we are having having all the knowledge of the local nodes, like if the node A is connected with other nodes 1, 2, 3, 4, then we will have the knowledge about those 4 nodes first, because they are our local nodes, they are connected to the A node. And what we mean from the global correlation, that it will combine all the connected nodes for that particular node, and it will like A is connected to 1, 2, 3, 4. Now 1, 2, 3, 4 is connected to now n number of nodes. So it collects all the knowledge from all the nodes and it generates a global. Summarize the global knowledge for that particular node. So and it is called mix hop, like it is called hopping for node by node. So let's move towards its algorithm so we can understand it better. This algorithmic overview is showing that the dual graph convolution consists of 2 parallel components. First is graph stage, which aggregates feature from immediate neighbors. Like as I mentioned, it aggregates the immediate neighbors information, and the M.GCN, which is multi-hop, it propagates information across multiple hops. So with each hop, it propagates the information across the nodes till it goes. So these are the mathematical formulas for each steps. We will understand it with the algorithm. So the graph stage aggregation per layer. For each node, aggregate from neighbors. Total operations across all edges will be big O of m into f into t, where the t is as we can see, what is the T here? The T is the time window size, number of time steps in input sequence. The weight transformation for that particular graph stage aggregation step, it will be big O of n into f square into t. If we can see, if we can look at it closely, we can understand that it is not something different from the other algorithm terms that we have studied earlier. It is same with this because the aggregation and the weight transformation, both steps are almost similar to the our previous steps, but they include one extra variable here, t. Now M.GCN propagation per layer is a sparse metric multiplication for n cross n matrix into n cross f cross t matrix. So for sparse graph, the complexity of that particular step will be big O of m into f into t. The next step is feature selection and fusion, combining outputs from L layers. Now we have L layers of convolution as we have discussed. We are combining the outputs from each layer. The complexity it generates is big O of L into n into f into t. Now next step is multi-layer processing, because this happens for all layers. So operations repeated for all layers. So we have to multiply whatever the total time complexity we are getting with L. So the final time complexity here will be big O of L into m into f into t, where n is number of nodes, sensors or location in the network, m is the number of edges in the road network graph, and t is the time window size, number of time the steps in input sequence. F is feature dimension and L is number of layers, as we have discussed. The next algorithm is TM-GCN ATD, traffic multi-hop GCN with attention. So the traffic multi-hop GCN with attention proposed by the author combines multi-hop graph convolution with self-attention mechanism for accurate traffic forecasting. The model uses a two-layer GCN to capture both immediate and multi-hop spatial dependencies in the road network, enabling it to understand how traffic conditions propagate across distant road segments. The integration of GRU with self-attention allows the model to focus on the most relevant historical time periods and neighboring locations, improving prediction accuracy for complex data patterns. So let's understand it with algorithm. This is two-layer GCN and it performs with a ReLU activation function, and as we can see, the A tilde here is our adjacency matrix, the W0 and W1 are weight matrix. So where F is the input feature matrix, size n into input features. A tilde is the adjacency matrix with self connection, size n cross n, sparse with m edges. W0 is the first weight matrix and W1 is the second weight matrix. So these are its dimensions, its sizes of the matrices. Now first step here, it includes the input feature transformation. For matrix multiplication, we are doing F into W0. So we will simply do the matrix multiplication for this step, n into F in, n cross F in into F in cross H. So for the complexity for that particular term will be big O of n into F in into H. So the second step for the same layer is the first neighborhood aggregation, which is whatever result we are getting here, we are multiplying it with our adjacency matrix. So the sparse matrix multiplication for that particular term is n cross n into n cross H. The complexity for that particular term will be big O of m into H. For the same layer, the ReLU activation function, it is element wise operation for n cross n H matrix, so it is big O of n into H, which is negligible. For second layer, we are having the same hidden feature transformation, H into W. We are having matrix multiplication with n cross H into H cross F out. The time complexity will be big O of n into H into F out. The next step for the same layer is second neighborhood aggregation. We will multiply whatever result we are getting, we will multiply it with our sparse matrix. So sparse matrix multiplication will be n cross n into n cross f out. The complexity will be big O of m into f out. In the next step, the final activation function happens element wise operation on n cross f out matrix. So the time complexity for the activation function, again it will be big O of n into f out, which is again a negligible term. So the final time complexity here will be big O of m into h plus n into f in into h plus n into h into f out plus m into f out. So let's simplify that the input features and output features, and let's take our term average features here. So the simplified time complexity will be of big O of m into f plus n into f into h. Let's see what it states. N is the number of nodes here, road segment in the networks. M is the number of edges, connections between road segments. F in and F out are input and output feature dimensions. F is the average feature dimension, as I mentioned. H is the hidden layer dimension. This is a comparative analysis of all the time complexities which we have seen for the traffic prediction, and we can see all the 5 algorithms and their respective time complexities here. These are the reference variable definitions. So from this table, what we can observe that the LT-GCN and GCN LSTM, these two, they share the same time complexity due to similar first order graph convolutional approach. The STAT-GCN introduces a temporal dependency explicitly via the variable t, which we have discussed earlier. So it has a term with t, and while MD-GCN combines both temporal and multi-layer factors. That's why the MD-GCN is having the term t, and for multiple layers it is having L. All algorithms leverage sparse graph structure. That's why the number of edges are very less than the dense graph, which is n square. So in this way, by using sparse matrix, we are making it for large scale road networks. We are making it efficient for the large scale road networks. So our domain for the traffic and transportation is completed here with all the time complexities mentioned. Now let's move towards the second part. The second part of our paper mentioned the algorithms related to computer vision and 3D reconstruction. So without wasting time, let's move towards the algorithms. The first algorithm we are having is adaptive GCN for hand pose estimation. The algorithm, what it is saying is the adaptive graph convolution network for hand pose estimation proposed by the author is designed to improve the 2D hand pose estimation by explicitly modeling relationship between hand joint points. The method uses a lightweight feature extraction network RexNet combined with a 3-layer adaptive GCN to enhance feature quality. Unlike traditional methods that treat joints independently, this algorithm leverages the natural graph structure of hand skeletons, where joints are nodes and connection between the joints form the edges. The adaptive GCN learns both the optimal adjacency matrix and weight matrix during training, allowing the network to automatically discover the most important relationship between joints to accurate pose estimation. This is the algorithm that they have used in that paper. The adaptive GCN layer operation for hand pose enhancement is H, which is input feature matrix with ReLU activation function. A tilde is an adjacency matrix which we will normalize with this term. By calculating this term, we will normalize it, and the normalized adjacency matrix will then become A cap. So the adjacency matrix into the input feature matrix and the weight matrix. These are the dimensions for their matrices. first step of this algorithm is adding the self connection, because each and every node is connected to itself as well. So for doing that, what we will do is we will add the identity matrix into the adjacency matrix. So we are adding the identity matrix into our adjacency matrix, so it is creating our new adjacency matrix A cap. It is just an element wise addition, so it will not create the and it is also a sparse matrix, so it will create the complexity big O of M. Next step, calculate and normalize adjacency matrix. Compute degree matrix and normalization of A, like this term which we have discussed. For this term, the time complexity again for sparse operations, it will become big O of M. The sparse matrix multiplication for adjacency matrix into the feature matrix will be the matrix multiplication between the matrix sizes of n cross n into n cross Fin. For sparse adjacency matrix with m edges, the time complexity for this matrix multiplication will be big O of M into Fin. The next step says about the feature transformation. Whatever result we are getting in this step, we will multiply it with the weight matrix. So the matrix multiplication will become n cross Fin into Fin cross Fout matrix. So the complexity we will have for this particular step will be big O of n into Fin into Fout. The ReLU activation function is an element-wise operation for n into n cross Fout matrix. So the time complexity it will show is the big O of n into Fout, which is negligible in respective of other terms. The last step is the multi-layer processing, because we are having multiple layers, L number of layers. So we will multiply whatever term we are getting, we will multiply it with L. So for final time complexity here will be, for a single GCN layer, the time complexity will be big O of M into Fin plus N into Fin into Fout. For the complete 3-layer GCN module, the complexity will be big O of L into M into F plus L into N into F square. Since L and N are small constants, where L is equal to 3 and N is equal to 21 for hand joints, so we can ignore the small constants. So the simplified time complexity will become big O of M into F plus F square. Here the N is showing the number of hand joints, 21, M is the number of edges in hand skeleton graph, Fin and Fout are input and output feature dimensions per node, F is the average feature dimension, and L is the number of layers. So that was the time complexity for the particular algorithm. Let's move towards the next algorithm in the same domain. This is a hybrid GCN Mamba for hyperspectral LiDAR classification. The dual feature attention hybrid GCN Mamba network, DSA-GNN, proposed by the authors combines graph convolutional networks with state space models for joint classification of hyperspectral images and LiDAR data. The GCN component captures local geometric spatial patterns by modeling relationships between neighboring pixels as graphs, where each pixel is a node and edge connected spatially adjacent pixels. The method uses a dynamic adjacency matrix derived from spatial coordinates to adaptively determine the pixel relationships. This approach achieves linear computational efficiency while maintaining the ability to model complex spatial dependencies crucial for accurate land cover classification in remote sensing applications. So let's understand better with the algorithm that they have used. The time complexity calculation of this particular algorithm will be like this. The GCN layer propagation rule is H, which is feature matrix, is equal to sigmoid activation function into A cap normalized adjacency matrix into feature matrix into weight matrix, where A cap is equal to this formula d tilde raised to minus 1 by 2 into a tilde into d tilde raised to minus 1 by 2, which is a normalized adjacency matrix of size n cross n, which is also a sparse matrix. H of L is the input feature matrix for that L particular layer. The H of L is the input feature matrix size n cross f in. F in are the number of input features. And WL is the trainable weight matrix of size f in into f out, where f out is the number of output features. So the first step in this algorithm will be feature transformation. For feature transformation step, what we are doing is we are multiplying the feature matrix with weight matrix, and the matrix multiplication will be like n cross f in into f in cross f out. The complexity for that particular matrix multiplication will be big O of n into f in into f out. Next step is graph propagation. In graph propagation, whatever result we are getting in our previous step, we are multiplying it with the our adjacency matrix. So the sparse matrix multiplication will be n cross n matrix into n cross f out matrix. The complexity for this particular matrix multiplication step will be big O of m into f out. The next step is activation function, which is element wise operation for n into f out matrix. The complexity for that particular step will obviously become big O of n into f out, which is negligible. So the final time complexity for this particular algorithm will be big O of n into f in into f out plus m into f out, assuming that the number of input features and the number of output features are same, and let's call it another variable average features f. The simplified time complexity for that particular algorithm will become big O of n into f square plus m into f. The variables here are saying that the n is the number of nodes, pixels in feature map. The m is the number of edges, spatial connection between each pixel. F in and f out, again input feature and output feature dimensions. F is the average feature dimension. So this is the time complexity for that particular algorithm. Let's move towards the next. Our next algorithm here is the LT-GCN, local and global feature fusion. The local and global GCN is proposed by this author, is a two-branch GCN architecture for hyperspectral image classification that achieves high accuracy with minimal parameters and short training time. The algorithm uses simple linear iterative clustering SLIC to create two graph structures: pixel level graphs for local features and super pixel level graph for global features. So we have seen a similar algorithm before as well, which is handling with the local and global features. So let's move towards its algorithm and let's understand what it is trying to convey. So the algorithm here, the fundamental GCN layer propagation is H for the layer L plus 1. The next layer is depending on the sigmoid activation function. This particular term, as we have mentioned multiple times, this is the normalized adjacency matrix into the feature matrix of the before the whatever layer was before, then this L plus 1 layer L, and the weight matrix for the previous layer. So this is the normalized adjacency matrix, size n cross n, sparse with m non-zero edges. H of L is the input feature matrix with size n cross f in, and WL is the weight matrix for size f in cross f out. Now let's move towards the algorithm and let's understand what it is trying to say. In first step, we will compute the normalized adjacency matrix Q. Pre-processing step using sparse operations, as we have mentioned earlier, to normalize the adjacency matrix, it takes order big O of m time, where m is the number of edges in that particular adjacency matrix. So it takes the big O of m, and this step is only performed once when we start the algorithm, so we don't have to repeat that algorithm with each epoch. So for the next step, what we are doing is we are doing the feature transformation. We will multiply the h of L with w of L. Matrix multiplication will be n cross f in into f in cross f out. The time complexity for that particular step will be big O of n into f in into f out. In the next step, we are doing the feature aggregation. Whatever result we are getting in the previous step, we are multiplying it with the whatever result we had with the normalized adjacency matrix Q. So the sparse matrix multiplication will be n cross n into n cross f out. So the complexity for that particular step will be big O of m into f out. The next step is the activation function, which is also element-wise operation on n cross f out matrix. So the complexity for that particular step will be big O of n into f out, which is negligible in respect to other terms. So the final time complexity of this algorithm will become big O of n into f in into f out plus m into f out. In this step, we will assume that the dimension of the input features and output features are same, and let's call it some other variable average features. So assuming f in is similar to f out is similar to f, so the simplified time complexity will become big O of n into f square plus m into f, where n is the number of nodes, pixels or superpixels in graph, m is the number of edges, connection between the nodes, and f in and f out are the input and output feature dimension, f is the average feature dimension. So this is the algorithm time complexity which we have derived. The next algorithm is VGAE with GCN, CONV, GCN convolution for 3D phase reconstruction. Okay, so what it says that the variational graph autoencoder with graph convolutional network layers proposed by the author is optimized for reconstructing high quality 3D phase meshes. The algorithm represents phase meshes as graphs where vertices become the nodes and mesh faces are converted to edges. The GCN con layer performs convolution directly on the graph structure, aggregating information from neighboring vertices through the graph's connectivity pattern. The VGAE uses a GCN encoder to learn latent representations of the phase geometry and the GCN decoder to reconstruct the mesh. This approach captures the intricate geometric relationships between the facial features better than traditional methods, enabling accurate reconstruction of diverse facial expressions and structures from limited training data. Let's understand it with the algorithm. The algorithm overview. The GCN con layer operation is x dash is equal to the normalized adjacency matrix into x into theta, where x dash is the feature matrix for our current layer, the x is the feature matrix for the previous layer, and the theta is the weight matrix for the previous layer. So this is the normalized adjacency matrix which we have discussed multiple times, so I am just skipping that step. Size n cross n sparse with m edges. X is the input feature matrix, size n cross f in, and theta is the weight matrix, size f in into f in cross f out. In the first step, we are adding the self connection because every node is connected to itself. So we are adding an identity matrix and we are normalizing it. So this takes the time we go off, and so this sparse operation only happens once when we start the algorithm. So the feature transformation here, x into theta, where x is the x theta is a matrix multiplication between n cross f in into f in cross f out. The complexity for that matrix multiplication will be big O of n into f in into f out. The next step is the graph convolution. So whatever result we are getting, we will multiply it with the A tilde. A tilde is our adjacency matrix. So sparse matrix multiplication will be n cross n into n cross f out. So the complexity, because it's a sparse matrix, it will become big O of m into f out. The final time complexity will be big O of n into f in into f out plus m into f out. In this step, we will assume that the input and output feature dimensions are almost same, and let's call them a variable f. So the simplified time complexity will become big O of n into f square plus m into f. The m is the number of nodes, vertices in a 3D phase mesh, in this particular research paper we had the number of nodes and the number of edges written in numerical form. So we have mentioned it. F in, F out, as I mentioned multiple times, input and output feature dimensions. F is the average feature dimension. So this is the time complexity for that particular algorithm. So now let's that is an end for that particular domain of computer vision. This is a comparative analysis of all time complexities of all the 4 papers which we had for the computer vision domain. So they are mentioned here. The common variable definitions are here. So what we can observe from this particular table is the 3 algorithms. These 3 algorithms they share the identical time complexity because the adaptive GCN has simplified, and this adaptive GCN, the hand pose, it has a simplified complexity m into f plus f square due to small constant values, because the number of n here was very small, it was 21. That's why it is a very simplified version of the algorithms that we have on later period. So values of n is equal to 21 joins, L is equal to 3 layers. All algorithms leverage sparse graph. That's why we are avoiding the dense graphs. We are having the number of edges and making them computationally efficient for large scale vision tasks. The complexity is dominated by either the feature transformation layer n into f square. When the n is very large, it will be n into f square. But when or by graph aggregation, when the graph is very dense, this will become n square. The mf will become n square f. So when the graph is when the graph is dense graph, the graph aggregation function m and m dot f will dominate. So that's an end for the second part of computer vision algorithms. So now let's move towards another domain, or third part, which is anomaly detection in cybersecurity. The GCN algorithm is widely used in cybersecurity domain as well. So let's understand the algorithms that I have found in this particular domain. The first algorithm is GCN for firewall log anomaly detection. The 2-layer GCN for firewall log anomaly detection proposed by the author addresses the challenge of identifying unusual network behaviors in complex campus networks. This model treats network traffic data as a graph where each node represents a connection event with features like IP addresses, packet size and protocol types. The edge represents the relationship between events. The GCN learns to classify each node as normal or anomalous by aggregating information from neighboring nodes through 2 convolutional layers, capturing both local patterns and broader network structure to detect security threats that traditional methods might miss. This is the algorithm. The 2-layer GCN performs forward propagation. There are 2 layers. In one layer we are using the redo activation function. In another layer we are using the softmax. Function. So activation function. So the A tilde is equal to, this particular term is used to normalize the adjacency matrix, which is n cross n matrix parsed with m non-zero entries. The X is the input feature matrix, n cross f and wl are the weight matrices. So for first layer we are having the feature transformation x into w of 0, the weight for the 0th layer, matrix multiplication of n cross f into f cross h. The complexity will become big O of n into f into h. For the second step, in the same layer, we are having the neighborhood aggregation. In the neighborhood aggregation part, whatever result we are getting in the previous step, we will multiply it with our adjacency matrix. So the sparse matrix multiplication will give the time complexity of big O of m into h. The next step is the redo activation function, which again the element wise operation, that's why it creates the complexity of big O of n into h. The next layer, the next step is for second layer. So for second layer we are having the same steps, the feature transformation, will be matrix multiplication between n cross h into h cross c matrices. The time complexity will become big O of n into h into c. The next step for the same layer is the neighborhood aggregation. Whatever result we are getting here, we will multiply it with our adjacency matrix. So it gives the time complexity big O of m into c. The next step in the same layer is softmax activation. Every activation function is element-wise operation, so it will also gives us the complexity of big O of n into c. Here, the c is the number of output classes because we are having normal or anomalous types of that particular cybersecurity attacks. So the c is the number of output classes. The final time complexity will be big O of m into h plus n into f into h plus n into h into n into h into c plus m into c. Let's simplify this step by assuming that the features which we have is the same as the number of output classes and the h is the dominant hidden dimension. So the time complexity will become big O of m into f plus n into f into h. So this is the particular time complexity for this algorithm. Let's move towards the next algorithm, which is GCN by LSTM for process anomaly detection. The GCN by LSTM model for process anomaly detection proposed by the author is designed to identify abnormalities in complex detection processes such as formaldehyde emission testing from wood panels. The model first constructs a graph representing the entire detection process where nodes include experimental stages, time windows and the equipment components, all connected based on their logical dependencies. The GCN component extracts the structural features by learning how different parts of the process interact, while the by-LSTM component captures the temporal patterns by analyzing how these features evolve over time, enabling the system to detect subtle deviations from the standard procedure caused by the equipment malfunction or operator errors. Let's understand this algorithm with our mathematical steps. The GCN component uses the first order approximation with two layers. So we are having two layer GCN here. So for each layer we are having the same formula which we have discussed many times. This is the feature matrix, this is the railway activation function, this is normalized adjacency matrix, this is again feature matrix and weight matrix. So this equation we know already. So let's move towards the first step. First step is feature transformation. In the feature transformation step, we are multiplying these two terms. The matrix multiplication for these two terms will give us the complexity of big O of n into f in into f out. In the next step of graph aggregation, or we can call it convolution, whatever result we are getting, we are multiplying it with our adjacency matrix. So it will give us, because the adjacency matrix is sparse matrix, we are getting the complexity big O of m into f out. The next step is activation function, which is again element wise operation. That's why it gives us the complexity of big O of n into f out. So and in each and every paper we are observing that the time complexity for the activation function, it is negligible. So for the next step, which is multi-layer processing, we are having L number of layers. So we will multiply whatever time complexity which we have derived, we will multiply it with L. So for a single layer we are getting the time complexity order of m into f out plus n into f in into f out. For L layers we will multiply this term and we will assume the f in and f out dimension will be the same as f. So we will have a simplified version here, big O of L into m into f plus n into f square. Since L is typically constant, like L can be 2 layer or 3 layer or 5 layer, the more simplified version of this algorithm will become, it gives the time complexity big O of m into f plus n into f square. Well, where n is the number of nodes, m is the number of edges, f in and f out are input and output feature dimension, f is the average feature dimension, and L is the number of GCN layers. So let's move towards the third algorithm, which is the spectral GCN for adversarial attack robustness. The spectral graph convolution network for node classification studied by the author in the context of adversarial attacks analyzes how GCNs perform when graph structure is intentionally manipulated by attackers. The model learns to classify nodes such as scientific papers in citation networks by aggregating features from neighboring nodes through spectral graph convolution. This research demonstrates how attackers can exploit network centrality measures to identify influential nodes and strategically add or remove edges to degrade the model performance, revealing important vulnerabilities in GCN-based security systems, highlighting the need for robust anomaly detection methods. So let's understand this algorithm. It is the same algorithm, the generic one. The standard GCN layer for node classification performs the sigmoid activation function, the adjacency matrix, and the matrix multiplication between the feature matrix and the weight matrix. So these are the terms: the adjacency matrix with m edges, n cross n, the feature matrix with n cross n, the WL is the weight matrix with the size f cross f. The first step will be feature transformation, will be the matrix multiplication between HL and FL, the H for the nth layer and W for the nth layer. The matrix multiplication will be n cross f into f cross f. The complexity which will be derived from this particular step will be big O of n into f square. In the next step, we will aggregate this with whatever result we are getting. We will multiply it with the adjacency matrix, which is obviously the sparse matrix. So for the sparse graph, we are getting the time complexity big O of m into f. The activation function is element-wise operation, so it will give us the complexity big O of n into f. The multi-layer processing, here we have n number of layers, so we will multiply whatever time complexity we have derived, we will multiply it with L. So for single layer, we are having big O of m into f plus n into f square. For L layers, we will have big O of L into this m into f plus n into f square. Since L is typically constant and a small constant, we can just ignore it, and this will be our simplified final time complexity. The n is the number of nodes, n is the number of edges, m is the feature dimensions, and L is the number of GCN layers. Now let's move towards the fourth algorithm in the same domain for cybersecurity. The dual graph convolutional network, dual GCN with adaptive weight learning and jamming attack recognition, proposed by the author, tackles the problem of recognizing jamming attacks on GNNs, the Global Navigation Satellite System. The model converts interference signals into a graph representation where nodes are signals, sample and edges represent the correlation based on the time and frequency domain characteristic. Unlike traditional CNNs that only capture local patterns, this dual GCN structure, it has two components: a weight learning module that adaptively determines how much importance to give to a different types of signal relationships, and a classification module using decoupling graph convolution (DGC) that prevents over smoothing while learning to distinguish between different types of jamming attacks with high accuracy and low computational cost. The time complexity calculation. Let's have the algorithm here. The DGC based classifier performs the softmax activation function. This is the feature matrix. The F is the feature dimension, A of K, where the K is the propagation depth, how deeply we want to propagate our information. It is defined as K. So A raised to K into X into W0, where X is the feature matrix of size n cross F, where W0 and W1 are the weight matrices for the particular layers. For the first step, we are having the feature propagation. So we are propagating the feature to the as we have discussed here, K is our propagation depth. So till which depth we are propagating our information, we are propagating the features. It will be the adjacency matrix K times. Each application will be n cross n into n cross f. So for the sparse graph, the time complexity which we will derive is big O of n k into m into f. The next step is the weight transformation. The weight transformation here will be z into w0 whatever result we are getting, we will multiply it with n cross f into f cross h. Complexity will become big O of n into f into h. The activation function is element wise decay loop, so we can ignore it. Its time complexity is negligible. The second weight transformation happens with the C, which is the number of classes. And which type of classes? Classes represents the attacks types. So the second weight transformation will be matrix multiplication between n cross h into h cross c. The complexity will become big O of n into h into c. The software classification here will be element wise operation. That's why the complexity big O of n into c is negligible. The final time complexity here we will derive is big O of k into m into f plus n into f into h plus n into h into c. Simplifying the terms, assuming the c is small and f is similar to the hidden layer dimension h, the time complexity which we will derive is big O of k into m of f, k into m into f plus n into m f into h, where the n is the number of nodes, m is the number of edges, f is the feature dimension, k is the feature propagation depth, h is the hidden layer dimension, c is the number of classes, types of attacks. So this is the time complexity for that particular algorithm. Now let's move towards the next algorithm. Next is the semi-supervised subdomain adaptation GCN for fault diagnosis, SSA-GCN. So let's dive directly towards this algorithm and how it works. Let's understand the algorithm that is used in that particular paper. So it extracts the features that remains meaningful across different conditions, while semi-supervised subdomain adaptation strategy aligns the distribution of the same fault types between different operating speeds using both unlabeled data and a small amount of labeled sample to achieve accurate fault diagnosis under time varying conditions, which is generic semi-supervised learning. So let's move towards our desired algorithm. The SSA-GCN uses two GCN layers with propagation formula this. Here, till this term, we are having the same as the previous layers, previous algorithms. We are having the same term, the normalized adjacency matrix, the feature matrix, and the weight matrix. Here we have this one particular extra term, which is a bias term, I guess. Yes, it's a bias term. So this is the normalized adjacency matrix. We will multiply it. The first will be feature transformation h into w, which will give our time complexity big O of n into f into f in into f out. The graph aggregation will become whatever result we have get here. We will multiply it with the normalized adjacency matrix, which is also a sparse matrix. So the time complexity here will be big O of m into f out. The bias addition and activation. Here we will add a bias of b. In each layer we will add a bias. So for nth layer, this is the bias b. So and the activation function, both these terms have the negligible time complexity, so we will just ignore that term. The multi-layer processing, because we have multiple layers in the GCN in this algorithm, so we will multiply whatever time complexity we are getting, we will multiply it with L. So the final time complexity will be, for single layer, of big O of m into f out plus n into f in into f out. For n layers, we will multiply this term with L and we will simplify the f in and f out. They are similar to f, and the simplified time complexity, because the L is a small constant which we can ignore. So the time complexity which we will derive is big O of m into f plus n into f square, where n is number of nodes, m is edges, f in and f out are input and output feature dimensions, f is the average feature dimension, L are the GCN layers. So here comes the end of all our time complexity analysis of algorithms which are in the cybersecurity domain. This is the comparison of all the algorithms which we have discussed, and the time complexities are mentioned here. What we can observe from this particular table is that the GCN by LSTM, spectral GCN and the SSA GCN share identical time complexities. As we can see, these three have the identical time complexities. the firewall GCN complexity depends on the hidden layer dimension H. The AWS, it is firewall GCN, it depends on the hidden layer H. That's why this H term is here. And the DSA introduces an additional factor K, propagation depth, which we have discussed earlier. All algorithms leverage sparse graph structure. So the DSA, you can see here, DSA has the K, the propagation depth factor, and they are all using sparse metrics. That's why we are getting the M term. If the for large scale anomaly detection cybersecurity application, the dominating term varies when the M into F is greater than N into F square, graph operations dominate, and otherwise the feature transformation dominates. So if M into F is larger than the N into F square, then the graph operations dominate, and otherwise the feature transformation dominates. So this is the observation from the particular algorithms. Now let's move towards the fourth part of our paper, which includes the algorithms with the domain of telecommunication and networking. Let's start with the first algorithm. First algorithm is GCN for 6G network slicing. What it states is the GCN based end-to-end slicing algorithm for 6G networks proposed by the author solves the problem of allocating network resources to meet extremely specific delay requirements for future services. Imagine different 6G applications like remote surgery, which needs ultra low delay, or video streaming, which tolerating high delay, and competing for the same network resources. This algorithm uses a graph like in video streaming. We can tolerate some delay, but we have the remote surgery. The doctor is sitting somewhere else and the operation is happening somewhere else. Then we need the latency very low. So to compete, both of those services compete for the same network resources. This algorithm uses the GCN to understand how network nodes, servers, routers are connected and intelligently decides where to place different service components to minimize end-to-end delay while satisfying each service's unique requirements. Like each service has its own unique requirements. We have to fulfill all of them. So how we can intelligently decide that where to place a different service component so that we can solve the diverge applications of the 6G networks. So this is a particular algorithm. It has the GCN layer-wise propagation, the same as we have discussed earlier. Feature matrix, sigmoid activation function, normalized adjacency matrix, feature matrix, and weight matrix. This is how we normalize our adjacency matrix. The feature transformation term, in which we are multiplying the feature matrix with weight matrix. It gives the time complexity big O of n into f square. The graph aggregation, whatever result we are getting here, we will multiply it with our adjacency matrix. So it will give, also the adjacency matrix is sparse, so we will get the with m edges we are getting big O of m into f time complexity. Activation function, it has the negligible time complexity because it's element wise operation. It gives the time complexity big O of n into f. The final time complexity will become big O of m into f plus n into f square. Here the n is number of nodes, m is number of edges, and f is feature dimension. This is very generic simple GCN algorithm used in this paper. The second algorithm is GCN LSTM for water distribution network monitoring. For water distribution proposed by the author predicts water pressure and flow rates across a network of pipes and sensors. Water networks are likely interconnected graphs where sensors at different locations influence each other. When pressure drops at one point, nearby sensor feel the impact. The GCN component learns these spatial relationships between the sensors based on the pipe network structure, while the LSTM component captures how water flow patterns change over time. This handles the spatial and this handles the temporal data, LSTM. So let's understand the whole algorithm. It includes the ReLU activation function. In this GCN layer, what we are doing is, this is our adjacency matrix, this is the ReLU activation function. We are multiplying the input feature matrix size n cross f, and the weight matrix size f cross h. H is hidden here, so it is hidden in dimensions. So for the graph convolution, what we will first do is we will multiply the adjacency matrix with features, input feature matrix. So the n cross n into n cross f. So for sparse graph with n m edges, we will get the big O of m into f. The feature transformation layer, whatever result we are getting, we will multiply it with weight matrix, which gives us the time complexity big O of n into f into h. The activation function has the negligible element-wise operation time complexity, which is big O of n into h. So the final time complexity will become big O of m into f plus n into f into h, where h is the hidden layer dimension, output features. So the next algorithm is GCN for 5G cooperative localization. The GCN based cooperative localization method for 5G networks proposed by the author helps mobile devices accurately determine their location in urban environments where GPS signals are weak and blocked by the buildings. Instead of each device working alone, devices share positioning information with their neighbors using 5G side link signals, device to device connection. The GCN processes these collaborative information by treating the network as a graph where each device is a node and connection represent which device can communicate with each other. By learning from angle and distance measurements between devices, the GCN achieves positioning accuracy under 1 meter while computing location in less than 10 milliseconds. So this particular algorithm is having we are having the phi, which is the activation function, which is not mentioned here or maybe mentioned somewhere else. So it is just an activation function. There is the adjacency matrix HL, which we are having common terms, feature transformation, matrix multiplication. The time complexity will be big O of n into f in into f out. Feature propagation, whatever result we are getting, the matrix multiplication happens here. Complexity will be big O of m into f out. The non-linear activation here, it is not a linear activation function, it is a non-linear activation function, but still it's an element-wise operation. So it gives the negligible time complexity big O of m n into f out. This is the multi-layer processing, so we will multiply it with L, whatever time complexity we are deriving, we will multiply it with L. The L we are getting here is very small constant, so we can neglect here L. So the time complexity, simplified time complexity is having this big O of m into f plus n into f square. So let's move towards the analysis of the time complexities for this particular domain of telecommunication. So here are all the 3 algorithms with their time complexities. 1 and 3 share the identical time complexities, as we can see, but this WN-GCN LSTM algorithm, it includes the hidden layer. So it has the hidden layer time complexity. So that's our observation for that particular domain. Let's move towards the next domain, which is recommender system and social networks. So the first algorithm in this particular domain of recommender system and social networks is the actor critic graph convolution networks, DSA GCN, proposed by the author and designed to improve recommender system by combining GCN with deep reinforcement learning. So we are using the reinforcement learning here. So what this algorithm is saying is also we could understand the critic GCN part. The critic part is a part of reinforcement learning. So we will see the algorithm here first. This is nothing but the feature matrix. This is sigmoid activation function. The alpha UV is the attention weight for the U and V are the each edge. For each edge, we are computing the attention weight alpha UV, and the HUV and the HU for the layer F is the embedding for node V at a layer N, and WL is the weight matrix F cross F. So we will compute the attention weights first. To compute the attention weights, we have to compute for each edge. So time complexity for each edge E, it will become big O of E into F. The next step is aggregate neighbor features. So we will aggregate it with it. So for each edge, multiply attention weight by neighbor embeddings. the weight aggregation happens, and the time complexity which we are getting here is big O of E into F. The linear transformation happens here. Whatever result we are getting, we will multiply it with the weight matrix. So the time complexity for that particular term will be big O of n into F square. The activation function is element wise negligible, big O of n into F. It is multi-layer, that's why we will also repeat it for L layers, and all operations will be repeated for T training epochs. Because it's a reinforcement learning, we have to make multiple epochs to learn the algorithm better. So the final time complexity will be big O of T into L into E into F, where this T and L are new variables, where L is the number of GCN layers, number of hops, and T is the number of training epochs, which is not mentioned in somewhere else. So this algorithm is different in its own. The next algorithm is SC-GCN, self-attentive core graph convolutional network, which is a learning based approach with graph GCN to capture the network topology combined with the self-attention mechanism to determine which users are most critical. This replaces traditional greedy algorithm with trainable neural network that learns the predict user importance based on the graph structure and partial solution. Here we are using the two-layer GCN operation. The first layer, we are multiplying the adjacency matrix with the feature matrix and the weight matrix. Then whatever result we are getting, we are applying the ReLU activation function in it, and then we are multiplying it with the adjacency matrix and the weight matrix again, and then again the activation function. So for the layer 1, we are doing the matrix multiplication of feature matrix into weight matrix. The time complexity will be given big O of n into F square. We have discussed it multiple times, so we don't have to do it for now. So the first graph convolution happens with this step when we multiply it with the adjacency matrix that we have. So for sparse adjacency matrix, the time complexity will be big O of E into F. For the third step, the ReLU activation function, negligible time complexity, big O of n into F. The next step, hidden feature transformation, which is for second layer. We are doing the whatever result we are getting, we will multiply it with W1. So the matrix multiplication will becomes like this, and the complexity will be given big O of n into F square. For next step, we are having the second graph convolution. The time complexity, whatever result we are getting, we are multiplying it with our sparse adjacency matrix. So the time complexity will be given big O of E into F, when E is the number of edges here. The self-attention pooling, this step is new, where D is the intermediate attention dimension, hyperparameter. D is a hyperparameter for intermediate attention dimension. So the self-attention pooling, this computes the attention weights D cross F into F cross N and aggregates it with attention R cross D into D cross N. So the total time complexity for this particular step will be big O of R into N, F into N. So for multiple steps, we are doing this. We are doing it in batch learning. So for each batch B, we are having the S steps. So the total steps we will have is S into B. So whatever time complexity we are having, we will multiply it with S into B. So this is the time complexity we have derived, and it is multiplied with S into B. So let's simplify it by since typically E into F and N into F square dominate. That's why the smaller terms will be neglected. Big O of S into B into E into F plus into F n into F square, where B is the batch size, D is the intermediate attention dimension, R is the attention dimension. So this is the new time complexity which we have derived from the particular algorithm. The third is GCGA, graph convolution with graph attention. It is a two-phase approach. First, applying the GCN to extract the structural features from the tourism network, and then using the graph attention mechanism to dynamically weight the importance of different relationships, so that the combination enables the personalized route recommendation by capturing both spatial relationship between attraction and user preferences for the tourism sector. So the time complexity calculation, we are having the algorithm the same generic algorithm, the sigmoid activation function, adjacency matrix, feature matrix, weight matrix, the feature transformation, we go of n into f square, the aggregation function, the sparse matrix, that's why we go of e into f, the activation function is element wise negligible, we go of n into f, multi-layer processing, that's why the L, we are having the L-GCN layers, but L is a small constant, so we will ignore it further in the step. So the final time complexity will be, we go of n into e into f plus n into f square. The comparison for all the three papers for the recommendation system and social networks is here. What we can observe is the SSC, GCN and GCGA, these two, they share the similar time iterations, they share the similar per iteration complexity of order of e into f plus n into f square, but this has the L layers and this has the batch size and the particular number of steps in each batch, so that's how they are differ. And the third algorithm is TLAF, which is also a simpler per layer complexity, which scales with the how the epochs are increased. It's a reinforcement algorithm, that's why there the number of epochs matter the most. The next domain in which we are entering is the emotion recognition. The first algorithm of emotion recognition is GCNN, the graph convolution multi-model model. The GCN processes this multimodal feature combination across time steps in convolution or sequence, allowing the model to understand how emotions evolve. The GCN algorithm which is used in this paper is again the same generic algorithm which is used in earlier papers, so we don't have to discuss it. I guess the aggregation function happens, it sparse matrix, it gives this time complexity, the transformation operation gives this time complexity, assuming the similar dimension f and f dash, we will have this time complexity. Activation function, again negligible term. Processing temporal sequence, for a sequence with t time steps, the graph has n is equal to 3t nodes, 3 feature combinations per time step, so all operations repeated for the sequence. So for sparse graph, typically in multimodal fusion, we are having this time complexity, but we have the n is equal to 3t, that's why here we will ignore the 3 constant and the expression will be this, where the t is the number of time steps, alternances or frames in the sequence. So the feature dimension, let's move towards the next algorithm, which is DSDIR, dynamic sparse directed graph convolutional network, which is different than the traditional GCNs. It is dynamically constructs a sparse directed graph that captures the directional flow of neural signals during emotional processing. What this algorithm doing is it is dynamically constructing a sparse directed graph. So, and then uses only the top k strongest connection to reduce the noise. So let's understand this bidirectional message passing algorithm. The dynamic graph construction will be like this. Here we are using the 10H activation function, here we are using the softmax activation function, and the top k element of sparse matrix. We will take the directed graph convolution, will follow the formula. The S with the right arrow and left arrow are normalized message parsing matrices, like in which direction the matrices are passing, the normalized messages are passing. So it is mentioned by the arrows. So it is again using the same x into w, a linear projection for graph construction. It is giving the complexity of big O of n into fl, the adjacency matrix calculation, GGT. It gives the, then because we are dynamically calculating the adjacency matrix, it will give the time complexity of big O of n square into L and not m, because this is not a sparse matrix. We are calculating it dynamically. That's why we have to check each and every node, connected to each and every node. That's why it is giving this. Now sparsification, we have to select only top k selections from the adjacency matrix. So the time complexity For that will be big O of n square into log k, where the log k can be negligible. So this is sparse matrix, so it results in m is equal to n into k edges. For sparse message passing, we are multiplying the s with the xl. The sparse matrix multiplication, we are multiplying the sparse adjacency matrix with xl. We will have the time complexity because it is two directional. The time complexity will be big O of 2 into m, but 2 is a constant, so the time complexity will be big O of m into f. The feature transformation will be n into f square, as we know. So because we are whatever result we are getting, we are multiplying it with the weight matrix. The channel attention mechanism, the global pooling in FCDRs have the big O of n into f, negligible compared to previous steps. Final time complexity will be this, and since graph construction n cross m square into L is typically the bottleneck, this simplifies into big O of n square L plus mf into big O of n square L plus mf plus nf square. K is the sparsity factor, number of connections retained per node. All the other terms are the same. This is the comparative analysis of time complexities of the motion recognition algorithms. So as we can observe here, the GCNN focuses on the efficiently fusing multimodal features across temporal sequences with having this time complexity, and this dynamic graph construction step, it increases the time complexity with big O of n square L, which dominates where L is large but benefits from specific sparsification that reduces the propagation cost from n square f to mf. Because it's a sparse matrix, we have sparsified it, so the n square will become big O of m into f. So that's how they have optimized the algorithm. Let's move towards the next part, the last part of our algorithm. In this part of our paper, we are having multiple algorithms with specific tasks. These are not the algorithms with the same domains. Each algorithm have their own different domain, so we cannot compare all these algorithms with each other. The following algorithms, which we are going to discuss now onwards, but they are also related to the GCN, so we are discussing that. The first is ST, Spatial Temporal Adaptive Cross Graph Convolution Fusion Network. What this algorithm is doing is, this is similar to the skeleton based abnormal gait recognition. Like it recognizes the posture in how we walk. So the algorithm addresses the limitation of traditional method by using graph fusion approach that combine both joints and bone representation of human skeleton data by fusing these two complementary graph structures through adaptive adjacency matrix and so on. Let's understand the algorithm to know it better. The core application, for each k layer, we are having the formula W into X into F. W is the weight matrix for the kth layer, X is the feature matrix, M is the adjacency matrix. XT is the feature matrix, size H cross N, M is the normalized adjacency matrix, N cross N, sparse matrix with E edges, WK is the weight matrix with size H dash into H. Till now we have used the term F in and F out. In this algorithm, they have used the term H dash and H. The feature propagation layer, the same mathematics will be applied here, and we will do that for the k partitions. So the matrix multiplication algorithm complexity will be big O of k into H into E. The feature transformation happens when we multiply the weight matrix with the whatever result we are getting here. It will give us the time complexity of big O of H dash into H into N. So we will repeat it for k partitions, so we will multiply the k with the step. We will aggregate across k partitions, so sum the results from all k partitions. Complexity will be big O of k into H dash into H, which is negligible. Apply across time dimension. Repeat operation for all t frames. Multiply total by t, and then multiply it with L because it's a multiple here. So we will multiply it with L, T, and the total time complexity is multiplied by K as well. So total time complexity here, which we will get, is order of, we go of L into T into K into H into E plus H dash into H into N, where H is the input feature dimension, H is the output feature dimension, T is the number of time frames, E is edges, N is nodes, K is the number of adjacency matrix partitions, number of partitions, and L is the number of layers. The next algorithm is the POI temperature prediction. So POI is point of interest, and in this complex heat source system, instead of reconstructing the entire temperature field, the model focuses only on the predicting the temperatures at essential locations. So how we will calculate the essential locations? This is the algorithm overview. We are using the leaky ReLU and batch normalization to normalize our adjacency matrix and leaky ReLU and activation function. So in this algorithm, HL is the feature matrix at layer L, size n cross f, S is the normalized adjacency matrix, and theta is the weight matrix. The pre-processing calculate the normalized adjacency matrix with this term. It only happens one time, gives this time complexity. Feature transformation happens when we we multiply the feature matrix with weight matrix. It gives the time complexity n into f square. The graph aggregation, whatever result we are getting, we are multiplying it with the sparse graph. That's why we are getting the time complexity. We go of E into f. The batch normalization and activation negligible term, we go of n into f. The residual connection, which is element wise addition, again which is also a negligible term, n into f. We will apply it across the k layers. That's why we are multiplying it with k. So whatever time complexity we are getting, we will multiply it with k, where the k is the layer. The next algorithm is sparse GCN for crop yield prediction. In this algorithm, we are using, we will systematically remove the edges based on the Fiedler number. What is the Fiedler number? Fiedler number is the second smallest eigenvalue of the Laplacian matrix, which measures graph connectivity. By using this approximation method, we have this algorithm. Let's understand what it is trying to say. The sparse GCN filtering operation for a single layer. For one layer, we are having the same H into L. H is feature matrix, W is weight matrix, E is our normalized adjacency matrix, sigma is sigmoid activation function. Feature transformation, same term which we have discussed multiple times. The complexity will be we go of n into f square. The graph filtering, whatever result we are getting, we will multiply it with the sparse graph. That's why we will get we go of E of edges of the sparse matrix into f. The activation function, it is a negligible term, element wise operation. So the final time complexity will be a number of edges in the sparse matrix into f plus n into f square. So comparison with the complete graph time complexity will be this, in which we will have the n square. In the sparse graph complexity will be like this. So the speed up will be n square by E of edges, number of edges. So that's how we have speed up the algorithm. These are the variable definition. Now let's move towards the next algorithm. Next algorithm is genetic algorithm with this GCN, which is also the same generic algorithm they have used in this paper. They are using two-layer GCN followed by a fully connected layer. So they have the two layers here of GCN, and they are a fully connected layer again with the bias term E. What they are doing is they are normalizing the adjacency matrix with this term, which we will have the order of the number of edges will be the time complexity. It is also only a one-time pre-processing term. Feature transformation, we will multiply the time complexity which we will have is we go of n into f1, where f is input feature dimension, f1 is output feature dimension. The graph aggregation function has the whatever result we are getting, we will multiply it with this. The complexity will be we go of e into f1. Then the activation function, negligible time complexity, we go of n into f1. The feature transformation for second layer, the same as above, we go of n into f1 into f2. So the F1, the output feature dimension of the previous previous layer will become the input dimension for this. So F1 becomes the input and F2 becomes the output feature dimension. Now the same steps will be mentioned here. We will multiply it. The activation function is negligible. For fully connected layers, we will have complexity will be big O of n into F2 into C. The C is the number of output classes. Here it is grade categories. So the final time complexity for this algorithm will be big O of E into F plus n into F into F1, which will become F square eventually. E into F1 plus n into F1 into F2 will become F square eventually, n into F2 into C. Now F1, F2 and C, let's assume that all of them, all the dimensions are similar. So it will become big O of E into F plus n into F square. Input feature dimension, first layer output dimension, second layer no output dimension. The fifth algorithm, GCN transformer for distribution networks. In this algorithm, we are transformer to capture long range dependency between buses. The trained model can quickly generate pseudo measurement unobservable buses using available PMU data, significantly improving system observability while reducing the measurement error from traditional 50% down to much lower level. In this algorithm, we are also using the same generic GCN algorithm, which we are not going to discuss for now. We are simply multiplying all the matrix terms and we will have the same time complexity for each and every step, which we have discussed earlier as well. We will have the final time complexity like this and the generic time complexity like this. The next algorithm is the GNN, redundancy eliminated GNN. In this algorithm, we are vertices in a graph, they share common neighbors. Standard GNNs repeatedly compute the same aggregations, which waste the computational resources. So what we are doing is we are reducing the redundancy. So in this algorithm, we are having the mathematical formula. We are doing the same thing. We are multiplying the aggregated features. The NV is the neighborhood of V, WV is weight matrix. We are multiplying it with feature vector as for now, and the step 1 will be the aggregation phase, which is the for each vertex V, the sum features from all neighbors, total operation across all edges will be big O of E into F. This is equivalent to sparse matrix vector multiplication. The second step is standard GCN, which we have discussed earlier. We are multiplying the step for all n vertices, we are having the time complexity big O of n into F square. For all layers, if we are applying the same, we will have to multiply it with L. So the time complexity which we are having is this. This is how the redundancy elimination aggregation is optimizing the GCN algorithms. Where theoretically the worst case which we are getting is this, because we are using the redundancy ratio here. So this is the time complexity for that particular algorithm. For the next algorithm, which is GCN, graph convolution networks with gating mechanism. So let's understand it with the example itself. In this algorithm, what we are doing, they have introduced a gating mechanism that learns to selectively merge information from different neighborhood orders, allowing the model to preserve important features from previous layers while incorporating new neighborhood information. So in this algorithm, what we are doing is we are using the 10H activation function. We are doing the same matrix multiplication here. We are having the same matrix multiplication here as well, and this is this symbol. It signifies the element-wise matrix multiplication or element-wise multiplication. Yes, which we have mentioned in this step as well. So this step, as the generic step suggested earlier, the time complexity for the feature transformation step will be big O of n into F square. The graph propagation will be big O of E into F, and the activation function will be negligible. The gate generation step, which will again the matrix multiplication complexity will be big O of n into F square. The gate activation is negligible term, big O of NF. The selective fusion, which is gating term, which is again the negligible term because it is also an element wise operation. That's why the time complexity NF is negligible. We will apply across all multiple layers. That's why we will multiply it with L. So the time complexity which we will derive is we go of L into EF plus NF square. The next algorithm is DSA GCN, time series enhanced with GCNs. In this algorithm, the relationship, the temporal patterns and spatial relationships between stocks, which is profitability, investment, extracted and temporal features are then combined with intrinsic stock characteristic by process through GCN layers to model mutual correlations across different stocks. So in this algorithm, we are using the same GCN algorithm, the adjacency matrix normalization term, the feature matrix, the weight matrix. We are having the feature transformation step H into W. We are having the complexity we go of N into F in into F out. The graph aggregation terms, whatever result we are getting, we will multiply it with the normalized adjacency matrix. That's why it becomes the B go of A into F out. The activation function here has the negligible time complexity N into F, apply across all layers. That's why we will multiply it with L. Whatever time complexity we are getting, we will multiply it with L. And the F in and F out are, let's suppose that they are similar to some term F. Then the simplified time complexity will be big O of L into NF square plus EF. Now let's move towards the comparative analysis of all the time complexity. Though we cannot compare the different domain time complexities, but they are using the same, majority of them are using the same generic GCN algorithms. We can say that we can take a look on their comparisons on their GCN implementations. So this is the table with all the 8 algorithms that we have discussed for the specific task for each algorithm. This is the algorithm. Most algorithms share the common, the generic E into F plus N into F square for single layer operations. Some of them are additional temporal dimension T, and the GNN and GCN and the multi-layer factors. All algorithms leverage the sparse graph structures, which makes the large scale application efficient. So, and these are all the papers that I referred for my research work. I also thank all the authors of these research papers, and I also thank my college to provide me this opportunity of the research and providing me the necessary resources for this research. So this was my term paper work for the data structure and algorithm subject, which I have mentioned in the video. My name is Soham Dave. My enrollment number is 25 MCD 005. Thank you.